So now what we're about to start here is my favorite subject. All right. I really enjoy this. This chapter and the next one are just some of the ones I enjoy the most. I think it is some of the most just clever and elegant things that are done in all of physics that you see. Very, very clever mathematics, very, very interesting ways to think about this. And hopefully I can impart to y'all some of the kind of conceptual abstract understandings that took me a while to pick up, but really made a big difference in this. Because when I took this subject at your level, it was my least favorite. I was dreading it then after I left general physics and went into the actual full course of electricity and magnetism. I was dreading it. I thought, oh no. None of it made any sense. I'm going to go take this class. It's going to be the thing that makes me not be able to be a physicist because there's no way I'm going to pass this class. It made no sense whatsoever. And I learned that there were certain concepts and ideas that were made apparent to me in the full course that were not made apparent in the general physics course. And I've never really understood why, because they were even just conceptual ideas that made understanding this and understanding what we were doing so much simpler. So I will attempt to impart those to you. I always do every time I teach it, and I really enjoy it. This is one of those subjects where there's some math, but there's more concept, and it's because the math in this actually gets pretty tricky. So we're not going to go, you don't end up going too crazy into the math like you would in a full course of it, but we will get into it, of course, some, but it's really neat, and the math is really neat. It's very clever. Okay, so let's get started here first with electric charges, forces, and fields. We're going to start with charges. So these pictures down at the bottom may or may not be something you've seen before, but you're going to see them as we do this, okay? And hopefully they'll start to make more sense to you. So what we're getting in here in this chapter is, first we'll do electric charge. We'll talk about insulators and conductors. I'm sure if you're in chemistry and stuff, you know that. And then Coulomb's law. When we reach that Coulomb's law, we are essentially done with the entire theory of electrostatics. All right, that's non-moving electric charges. And that is it. So in other words, this part right here, we're done with it. There at that point should technically be no electrostatic problem in the universe that you could not solve. The problem is, do you have enough time to solve it? And the answer is most likely, no, you don't. All right, because doing it with just this would take you, could take you thousands, millions of years. You'd have to sit there and work out a problem by hand. Of course, then that is probably going to change a moment later, and then you have to start over. So think of that as like learning how to add, right? You learn how to add, and once you know how to add, you can pretty much do anything in math, right? And from that point on, like when you learn multiplication, it's just a way to do repeated addition. Right? If we're doing 2 times 3, it's pretty easy just to do 2 plus 2 plus 2, right? But if you're doing like 571,432 times 685,940, if you're doing numbers like that, you're not going to sit there and add those up that many times. It takes way too long. So you learn the math trick of multiplication. It's a way to do a lot of addition very quickly. And so when we start getting into this stuff down here, like the electric field, and even the next chapter, we'll talk about voltage, it's a way to do a lot of the math quickly for everything that basically just stops here. So you go through Coulomb's law, and that tells you what you need to know, but it becomes very difficult to solve problems that way, mathematically speaking. So we'll introduce the idea of an electric field that'll allow us to do a bunch of problems basically simultaneously. And you'll see what I mean when I get that. And then in the next chapter, we'll introduce voltage, which allows us to do a bunch of problems simultaneously, but even easier than the electric field does. So like the main way this works is you start off with a problem, usually, where you have some sort of idea where you want to know about charges, and you have Coulomb's law. And you take and you convert that situation into an electric field situation. And then you take that electric field situation and you convert it into a voltage situation. And then you solve it very easily with voltage. And then you convert it back to electric field and then back to Coulomb force. The Coulomb law is our force, and suddenly we know what's happening. And if we didn't do that, it would take us way longer to try and do it just with Coulomb's law. Okay, so that's what we're going to see as we do this. So let's start with electric charge. First time we saw this was static electricity. If you've ever rubbed a balloon on your head, if you've ever in the winter when it's not super humid, rubbed your feet on the carpet and then shocked somebody or touched something and shocked you, or if you've ever noticed the little signs on the gas pump that tell you not to get in and out of your car while you're pumping gas because you might rub up against the seat, build up a static charge, and then walk over and touch the gas pump and have a spark go off and set a fire. No, if you want to see it, I guarantee you can find multiple examples of this happening on YouTube. In fact, I used to show it to students. Don't do that. Don't get in and out of your car because you can start fire. Usually it was a lady and she got back in her car and then she got out and she didn't touch anything and she went around and touched the handle and it sparked and it went up on fire right there. So you have to be careful with that. If you do get in and out of your car, go touch something metal to get rid of that spark before you touch the gas pump. Okay? Now a lot of you are like, oops, you're in Florida, it's very humid here, so it doesn't happen as much, but in the winter, you got to really be careful here, or if you're up north. Sometimes, yes, but you don't want to do that. The other thing you have to be really careful with, and if you ever have a gas can, tells you there should be labels, warnings on there telling you take it out of your car and set it on the ground. Because if you leave it in your car, all that rushing in gas and you putting the handle in and out can build up a charge in there. And I once saw a video of a guy who had his back of his truck had a bunch of gas cans in it, and he's filling one up, and then he just took it out and filled up the next, and he got to one of them and he pulled it out and it sparked. And it just like ignited the whole back of his pickup truck. So you have to be careful with that kind of stuff. There is static charges that can build up. Rub a balloon on your head, it makes your hair stand up. Rub a balloon on your head, hold it near a tiny thin stream of water, and the thin stream of water goes over to it. All right, that is static electricity, or static charges. You can see here they're talking about after being rubbed on a piece of fur, an amber rod acquires a charge and can attract small objects. And we'll talk about more why that happens, but most people have experienced that, right? Like with the balloons or static clothes coming out of the dryer and stuff like that. So here, charging both the amber and glass rod shows that there are two types of charge, of electric charge. Like charges repel and opposites attract. So we're calling this charge, but I want you to think of it a little differently. And in fact, this is the way it used to be thought of and used to be called, is not calling it electric charge, but we're going to replace that word charge with mass. Think of this as electric mass. So the mass that we had before determined the electric force, or not the electric force, the gravitational force. Okay? Like whatever that was, I know y'all didn't quite do it, but there it was. The amount of mass you has, it tells you the gravitational force. Here, the amount of charge you have is going to tell us the electric force. So it's in a very similar type of situation to the gravitational mass. In fact, gravitational mass looks like this. And there are the two masses up there over the distance squared. Electric mass in the Coulomb's law looks like this. In fact, I'll just put this there, the Coulomb constant, Q1, Q2. We use Q's for it, but look how similar in form they are. The Q1 and Q2 are the electric charges, which you could think of as electric mass. They play that same role. The only big difference here is that with masses, we only have one type, at least that we know of right now. We just have one type of mass, and that's all mass that's just attracted to other mass. With electric charge, there seems to be two types. All right, there's two types. They were named positive and negative, I believe, by Benjamin Franklin, and they are simply names to indicate that they are opposites of each other. The names could have gone the other way too. It could have been that you could just flip-flop the names. Like I think we all pretty much know protons are positive, electrons are negative. And it very easily could have gone the other way. They were just named. They're opposite. It's just to show they're opposites. right? You could have named them up and down or whatever, okay? And so it shows their opposites. And so what we end up with here is both an attractive type force and a repulsive type force, all right? If you have two charges that are same, both positive charges, they repel. If you have two charges that are opposites, they attract. So it's like that old saying, opposites attract. Opposite charges attract, like charges repel. Okay, that's the main idea there. But it's like our electric mass, again, except we have two types of it. So we'll get both a repulsive force and an attractive force. All electrons have exactly the same charge. All right, that is what we have found. No one has gotten there to be an electron with a different charge. In fact, there was something called the Milliken oil drop experiment, where essentially you spray a bunch of these little oil droplets out and you give them a random amount of charge. And then you let them fall under gravity, and then you apply an electric field to them and you watch them rise, and you can calculate how much electric charge they have. Okay? And by doing that for lots and lots and lots of different little tiny droplets of oil, you can start to see you only end up with certain types of amounts. Okay, kind of like if all I kept doing was handing you like boxes full of random numbers of coins. No half coins, no anything like that. You could eventually start finding the differences between the masses of the boxes of coins and eventually figure out what the mass is of a single coin, because you're never going to get a division smaller than that, right? And so that's essentially what the Milliken oil drop did, is he found that no matter what he did, all the math, all the charges he kept coming up with were some sort of integer multiple of that right there. 1.6 times 10 to the negative 19th coulombs. It's a very small amount of charge, but they all have that same one. And it's called the Coulomb. Okay? And that's what every electron has. Every proton has that same charge, but positive. And so any of the amounts of charge you come across should be exactly evenly divisible by that, because it's a certain number of electrons and protons together adding up to make that. I had to do this Milliken oil drop experiment, worst experiment I ever had to do. These tiny little droplets, you're in there and you're in this dark room and you're staring into this little people, watching a little droplet as you're making it go up and down, trying to time it and make its measurements as it goes past these lines. If you are not perfectly balanced, that little oil droplet that you have to watch go up and down like 20 times, you watch it go up and down like 5 times, and then it slowly goes out of focus and you've lost it and you have to start over. And you've got one good and you're like, yes, I'm up to like 10 times. And then someone walks across the room and your whole machine goes like this and all the oil droplets go everywhere. Or someone closes the door and all your oil droplets go like that and they're gone. I spent a week in there. Every hour I could spend, I got the 10 to the negative 19th and I was happy. And in fact, the professor told us, if you get the order of magnitude right before this is due in your week that you have to work on this, you're good, you can stop. So my total respect to him. I can't imagine how many days and days and days and days and days he spent doing this to actually get this number consistently. Crazy. But there it is. So we have that quantization of charge right there. Okay, so it's the same for all of them, and that's what gives it to us. Okay, any questions on that? All right, and that's also called the fundamental charge, like that little lowercase letter e that we use to represent it is just the charge of an electron. Have y'all ever seen that before? A little e? Yeah, like E minus, E plus, and stuff like that. There you go. That's it. Here, the electrons in an atom are in a cloud surrounding the nucleus and can be separated from the atom with relative ease. This is where we had that gold foil experiment where they first thought that electric charges, positives and negatives, were more like, I think they called it the plum pudding model, where they just had electric or positive, negative just randomly all distributed throughout the atom. But then the gold foil experiment came along and showed that it was not the case. They fired, I believe, cathode rays at the gold foil, and they pretty much should have just passed right through, slightly deflected. But they found that that was mostly the case. Most of them just passed through and would come off at like a slight little angle, but every once in a while, one would bounce back. And so the idea then had to come on that there had to be something very dense in there to reflect them back. And that's where this kind of molecule with very dense positive cores and a very undense outer cloud of the negative electrons. Okay? So you have that positively charged nucleus and then the negatively charged electrons on the outer surface. Here, talking about amber rod again, if you rub it with some fur, some of the electrons on the atoms in the fur are transferred to the amber. What this does is makes the amber negatively charged. All right, you have then an overabundance of negative electrons. You have more of them than you do the positive protons, and therefore you end up with a total net negative charge. Right now, pretty much everybody in here has what kind of a charge? What's your charge right now of you or these chairs in here or anything? What is it? Yeah, neutral, it's 0, right? So they act just like positive and negative numbers. Right now you have just about as many electrons as you do protons, so you're neutral. But if you get an overabundance of one over the other, then you get that charge. You get too many electrons, you become negatively charged. You lose too many electrons. You don't usually lose the protons because they're down in the nucleus. But you lose electrons, you become positively charged. Okay? Here, we find that the total electric charge of the universe is constant. It's okay.
Okay, so for like the slide before, so why was the amber negative and then like the wool positive? Like, could it be either way?
Not in that case, because one of them is very good at gaining electrons and one of them is very good at losing them.
Okay.
So, yes. And so the fur is losing electrons and becoming positive, and the rod is gaining electrons, therefore, and becoming negative.
Okay.
But they're still the same. The chemical composition is unchanged. It's just the electrons that have been shifted through non-covalent type forces. And then these two things would be somewhat attracted to each other then as well through non-covalent forces.
Okay.
Yep. But it's still the same total number of electrons, which is what I was about to say right there, is that what we have found so far, at least locally, because all these conservations we know locally, is that electric charge is conserved. Does anybody know what it is that gives us conservations? Like last semester, y'all had like conservation of momentum and conservation of angular momentum and had those different things. Conservation of energy. Does anybody know what fundamental thing causes a conservation? Huh? Not really just a closed system. It helps, I guess, if it is. But there's a reason that it is returned at the end, I guess. Not entropy, maybe. It's symmetry. It's symmetry. So imagine you're sitting in a still pool of water, right? None of it, there's no flow, the water isn't moving all around. If you take like a float that's floating in the pool and you push it with a certain amount of force one direction, it's going to go just as fast in that direction as it would in any other direction that you pushed it with that same force, correct? Because the water is the same in all directions, right? There's no preference direction. But now let's put you in a flowing river. If you push that raft in different directions, is it going to go the same amount away from you at the same speed in every direction? No, if you're pushing it upstream, it's not going to go away from you very fast. In fact, it might even come back at you, right? Versus pushing it downstream, it's going to go away from you a lot faster. Okay? So inside the river, when you don't have that symmetry, you actually have a flow going, you end up with, you don't end up with a conservation of your momentum as you push the raft. If you're in the nice still pool, you have that kind of conservation because it's the same in all directions. It's isotropic. Okay? Anybody know what symmetry causes you to conserve energy? Time. It's the idea that things are the same, that the laws of physics are the same yesterday as they are today, as they will be 2 days from now. Time symmetry causes that. Spatial symmetry Like moving causes conservation of momentum, like with the pool. It doesn't matter which direction you push it in, it's the same. It has no preference. And then same thing with the spatial. It also doesn't care if something is spinning. It's the same for all spinning, so you get that conservation of spinning, of angular momentum. There is a conservation, or there is a symmetry that allows, I think it's a phase that allows electric charge to be conserved, and it is conserved, okay? So whatever the amount of electric charge you start off with, like back here on this one, if we looked at it and said, here, we have a total electric charge of 0, both of these things are neutral, what's our total electric charge there? 0 still, right? So this might have been, you know, Q equals 0, Q equals 0, but down here, Q equals like plus 5 coulombs, and then this one would be, any guesses? -5 coulombs. All right, whatever it would have you. I'm just making numbers up, but you see what I'm saying on that? And it would still be a total of 0. So charge is conserved. All right. And as I already stated before, it is quantized in units of E, the 1.6 times 10 to the -19th coulombs. Okay. Any questions on that so far? So you really have to think about that when they start to say, oh, I have this object with this charge and this object with this charge, and I put them together so that charge can go freely between them. It's gonna try to equalize where you get the same amount of charge on both. If you did it with this, it'd go back to being 0. But say you had something like, you know, -10 coulombs, and you put those two together and charge flowed freely between them, they'd each end up with -2.5 coulombs. It would split, whatever the total was, would split evenly between them, assuming shape doesn't matter. If shape starts to play a role, then we'll talk about that later too. All right. Gaining electrons makes you negatively charged. Losing electrons makes you positively charged. Here, electric charge. Some materials can become polarized. This means that their atoms rotate in response to an external charge. This is how a charged object can attract a neutral one. Who remembered what I said about rubbing a balloon on your head and holding it near a thin stream of water? What happens? Water goes through it. Anybody ever tried that? Have you? And it does, doesn't it? And how does an atom or molecule of water look? Polar, right? Because you have like the oxygen, you have your 2 hydrogens over like this, right? And then what's over here? This is the way it used to always be drawn in my day. You have electrons, right? And so you have a negative side and a positive side, right? Huh? Partially?
They just draw like a little it's a partial positive and partial negative.
You either have more positive, of course, there's always some canceling out. Yes, there are still electrons on the other side, but you have an abundance of electrons on one side, and therefore a deficit of electrons on the other side. Therefore, you have a positive side and a negative side.
Yeah, they just call it partial.
Because shares electrons, that's why.
All right. All we care about here is, we don't care about the ones that cancel out. We just care about the abundance. And so you end up with something polar, and it'll attract over because it will rotate and align itself such that this occurs. And you can see that here in this picture. If you have these polar molecules or polar atoms, they can arrange themselves like that. So we bring something positive near it. The negative side would attract over to it. The positive side would repel away from it. And you'd end up with this total, what is called a surface charge here. Because if you notice inside, I have positive, negative right there. That's basically going to cancel out, right? Everywhere, positive, negatives. These are all canceling out from atom to atom or molecule to molecule. Where it doesn't cancel out is where? Over here on the surface. And so you end up with this surface charge, which is what allows you, if you rub a balloon and hit it and hold it over like some confetti or something, and the confetti will come up to it because it will polarize like that. And then the side that's closest will attract to it. We haven't talked about it, but essentially the further something is away, the less of an electric force there is, and the closer it is, the greater it is. So these negative charges over here are closer to our positive rod than these are further away. So there's a greater attractive force than there is a repulsive force.
I like this chapter. Yeah. Like chemistry.
Oh, just wait. All right, now, insulators and conductors. I think we should mostly know this one too, chemistry people. Conductors is a material whose conduction electrons are free to move throughout it. That means that the valence electrons are up, they have an energy gap. Anybody know what causes that energy band gap? Chemistry people? That allows for the valence electrons to be free to move in a conductor, which is typically a metal. It's something about the shells. Why is there a band gap in the metals and not in the non-metals? But why is there that big gap in energy?
Oh, it's because of SPDF.
So you end up with, you have these electrons that are in these lower ones, and then in a metal, you have a big band gap, and then you have these other electrons up here, and they are up above the conduction band where they are not held on to very strongly, and they can flow around from atom to atom. In the insulators, you don't have that. They just start stacking right on top of each other like that, and you don't end up with this big gap here called a band gap. Do we know why that band gap exists?
Yeah, isn't it like the SPDF?
Kind of. It's because the orbitals cause destructive interference in these metals, and you end up with this big gap that occurs in there. So it's actually a wave interference that causes it. Just in case y'all were wondering, since we just did wave interference in the last chapter. You don't need to know that right now. Just throwing out something interesting for you. Essentially what you need to know at this level is valence electrons, the outer electrons for metals, they are free to move for the most part. They flow around easily. A lot of times, somewhat accurately in some situations, it's modeled as an electron gas where they can just kind of flow all through the metal. And in an insulator, this is not the case. You can get them to flow, right? Lightning can strike through the air, even though the air is not a metal, it's not a conductor, right? But it takes a lot of energy to make that happen. So these conduct materials, these conduct electricity easily, these do not. By the way, which one of these two things transfers heat more easily? The conductors. Why is that? Because the electrons are the largest carriers of thermal energy. And if it can conduct electricity easily, it can conduct heat easily. All right. So metals and nonmetals. If a conductor carries excess charge, the excess charge is distributed over the surface of the conductor. If you think about this, all the charge is free to move, right? And if it wants to spread out, all the negative charges, these excess negative charges are all repelled by each other. How do they get the furthest away from each other? Yeah, they go out to the outer edges, right? They want to get away from each other. That's where it's going to happen. If you try to cram them all in the middle, they repel off of each other. And so they get as far away from each other as they can by going to the surface. And so excess charge on a conductor will reside on the surface. All right. Semiconductors. All right. These are those wonderful things that can act like a conductor or an insulator depending upon their impurities, right? You can dope a semiconductor with impurities to make it either a conductor or not, right? N and P type semiconductors, depending on how you dope them. We don't really need to know that too much here, but and then there's the photoconductive ones that become conductive when light shines on them. All right, so you have different kinds of things that can be both conductors or insulators depending on the situation. All right, and those are those ones that tend to be between the metals and non-metals, right? Where all the semiconductors are. Here we go. We're about to finish electrostatics. Coulomb's law gives the force between 2 point charges. 2 point charges. The electric force between them is equal to K, what is called the Coulomb constant. All right, 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. If you can't remember those units, it's the only units that will make the units on both sides equal each other. All right, it's a Newton that gives you the force. It's a meter squared to cancel in the numerator that cancels with the meter squared of the R squared, and it's a Coulomb squared to cancel with the 2 coulombs that you get in the numerator and leave you with just a Newton, which is a force. So that's a constant of proportionality. It actually contains a 4 pi inside of it, so that this is 4 pi R squared in the bottom, telling us we have spherical symmetry here. That the electric field, we haven't used that term yet, I shouldn't say it. The electric force spreads out on the surface of a sphere. All right, another way this is often written is 1 over 4 pi epsilon naught Q1, Q2, they like the absolute values, so I'll put them in there. Q1, Q2 over R squared, where that Coulomb constant K equals 1 over 4 pi epsilon naught, but then you see 4 pi R squared. That's the surface area of a sphere. So as we move out, we have that spherical symmetry in this, and we get it lessening by 1 over R squared, as it, like we talked about before. I talked about the sound, right? Like you blow up a balloon and it gets lighter and lighter and lighter. So it's going to have that 1 over R squared dependence as well. That epsilon naught is called the permittivity of free space. I don't know that you really need to know that right now. You can pretty much just stick with the Coulomb constant. Okay, but if you get into higher level stuff, you start using that epsilon naught rather than the Coulomb constant. Okay, the force is along the line connecting the charges. It is attractive if the charges are opposite and repulsive if the charges are like. This is a force. It is therefore a vector and has a direction. If you're working with vectors, they're a pain, right? And that's why we're going to work our way up to voltage, which is a scalar, and make things easier to work with. Okay, that's what I was talking about earlier before. So this is a vector. It can be kind of a pain. You look at 2 objects, you say, all right, I have the charge on this object, I have the charge on this object. There are 2 little point charges. You measure the distance from one center to the other one's center. That's R. You plug in the charges, you plug in 8.99 times 10 to the 9th Newton meters squared per Coulomb squared for the Coulomb constant. You multiply it all together, and that tells you right there the force on them. This with the absolute values does not, and I like it with the absolute values, does not tell you whether or not it's an attractive or repulsive force. At that point, you need to look and see, was it a positive charge and a positive charge? Then it's repulsive. They're pushing away from each other. Was it a negative charge and a negative charge? It's repulsive. They're pushing away from each other. Was it a positive charge and a negative charge? It's attractive. They're pulling toward each other. So you may have the same sort of things. If I have a positive charge and a positive charge, I'm going to get my force like this. If I have a negative and a negative, I'm going to have a repulsive force. If I have a positive and a negative, they're going to attract like that. Now, who remembers Newton's laws? Huh? Sorta? What was the first law? Brilliant. Yes, it's kind of. An object in motion remains in motion. An object at rest remains at rest unless acted upon by a net external force, right? You can't reach down and pick yourself up by your feet. That's an internal force. Has to be a net external force. What was the second law? Good, F equals ma. What was the third law? For every force, there's an equal and opposite force, or for every action, there's a equal and opposite reaction. That's just referring to a force as an action. So here, if we use this to calculate the force on one of these, it's also the force on the other, right? Just in the opposite direction, which you can see here in my picture. If this is 2 newtons to the right, this is negative 2 newtons to the left, kind of a thing, okay? So, keep that third law in mind when two objects are applying force on each other, the equal and opposite force still applies here. All right. Oh, here's the picture I just drew. There you go. Better than what I did. Forgot that was there. So Coulomb's law, the forces on the two charges are action-reaction forces. The force of 1 on 2 is equal to the force of 2 on 1, just in the opposite direction. Okay? Any questions on any of this so far? No? All right. Superposition. We all heard that word before? We talked about it with waves, right? I don't know if you talked about it last semester or not. But the way we figure out the way two waves combine is we superimpose them. We use the superposition principle, which means you just put them together. All the crests and the parts above equilibrium act like positive numbers. The parts below equilibrium act like negative numbers, and you just add them all up. Well, the superposition principle works here as well. We have Coulomb's law that allows you to find the force between any two charges. So here, what we can do, if we want to find the total net force on one single charge due to multiple other charges, you simply calculate each one's force individually and then add them up. Now, the problem is they are vectors, and so you have to add them like vectors. So if you look at this picture here, all the forces acting on Q1 are simply the force of charge 4 on Q1, the force of charge 3 on charge 1, and the force of charge 2 on charge 1. So we can say F net on that one, right? In fact, actually, we can just say net force acting on charge 1 is force of 1 on 4 plus force of 3, force of 1, 3 plus F1, 2. And then we have to be sure to remember these are vectors when you add them. So you can't just add up their numbers. You have to worry about the angles they're at and all that kind of stuff and do that wonderful, you know, if they're at right angles, you're lucky. If they're in a straight line with each other, you're even luckier. If they're not, then you better know your like laws of cosines and laws of sines, right? And start going through and doing them. But this would be it. And then the overall net force, of course, still going back to Newton's second law, would be MA, and you could tell what that charge was going to do. Right? So you'd come over here, you line the forces all up, tail to tip, right? Just like you did before. I always said this, you line them up in a walkable path. If you can only walk in the direction of the arrows and you have to start from the first one and walk all the way to the end, you have to be able to walk along the path. So this is a walkable path, right? I can walk along that one in the right direction, walk along that one, walk along that one. Had you done something like F3, you know, if you line them up like that, this is not a walkable path, because if I start here and I walk to the end of this one, I'm suddenly in the wrong direction for that next arrow. Okay, you can't walk in the wrong direction. It's like if you're at like a, you know, like an airport where you have the arrows on the ground. You got to walk in the direction they're pointed, right? So arrange them in a walkable path. I don't know if that helps. Just tail to tip the whole way. Add them up. Doesn't matter which order you do. Some orders might be easier than others. And then you have to add them up. And even with just these three here, this would be a fairly long problem, right? Now let's go into a situation where you don't have 4 charges you're worried about, but instead you have a mole of charges. How many charges would you have? How many electrons would you have if you had a mole of electrons? Good. 6.022 times 10 to the 23rd electrons. And if you had all of those acting on one single electron, it would take you, and they say they were all just spread out or even not spread. They're on the surface of a sphere or something. That's a hard problem to work out by hand and add up all those vectors, isn't it? Especially considering a moment later, that one electron, if it's free to move, it's either going to be pulled closer or pushed further away. And then you got to redo the whole problem again, right? And you can see how this Coulomb's law, technically speaking, we should be able to do any problem we want with any shape. If we're good enough and meticulous enough and fast enough at doing this, we should be able to solve any one we want. But the problem is it's not practical, right? It's way too difficult to do that. We can do it for some simple problems, but when you get to more and more complicated situations, more realistic situations, pretty much becomes undoable, right? All right, so superposition principle, solve the forces all on the one you're trying to find the force on, find it all individually, add up the forces. Just make sure you're treating them as vectors. Okay, so you have to pay close attention to directions and signs, like say this one right here was actually a negative charge, then suddenly this right here would be pointed in this direction. And you have to be careful that you get the directions pointed right and all the angles and all that kind of stuff. So it can be quite cumbersome, difficult, painstaking. Anyway, so Coulomb's law is stated in terms of point charges, but it is also valid for spherically symmetric charge distributions, as long as the distance is measured from the center of the sphere. So even if we go back to a situation like, where was it? This one, where we have the charge distributed on the surface of sphere, we can still use Coulomb's law here. We just treat it as though all this charge was actually located right at the center of our sphere. If we do not have a spherical distribution of charges, then we can't just use, you can use Coulomb's law, it's just you then have to also invoke calculus. All right? It's just that if you try to invoke a calculus here to add them all up, right, it's just going to turn out to give you the result as though they were all at the center. And so you can kind of just skip that and do it. In fact, later on when we get in the electric fields, I'll even show you a good, it's calculus done, but I'm going to explain it conceptually, like type of proof to make you agree with me that they would all act as though they were centered at the center of the sphere if they were evenly distributed. Okay, it'll be interesting. We'll talk about overflowing bathtubs, and I'll show it to you with that. Okay, electric field. Now we're getting into the math tricks. All right, essentially, that is what this electric field is. It is essentially a math trick. However, I will highly encourage you to think of it as a real thing. Think of it as a real thing. It is not necessarily a real thing, but we're going to pretend it is. So let's think of the problem that this is going to fix. All right, let's say that Casey back there had a certain amount of charge, right? And Casey had some charge, and Fan had some charge, and Michael had some charge, and I had some charge up here I was standing with. And I wanted to know what the force was of all their charges on my little clump of charge up here. So I take Michael's, and I say, all right, I do the Coulomb's law on it, F equals K Q1 Q2 over R squared. I find and measure my angle, and I get this force, right? Obviously a repulsive force in this case. I mean, it's Michael, right? So, yeah. So I do the whole Coulomb's law, and I figure out what his force is on my charge. And then I take Casey's, and I do F equals K Q1 Q2 over R squared, measure all my angles, figure out what the overall force is. And then I do Fan's, and I do F equals K Q1 Q2 over R squared, and I figure out what the total force is and the angles and all that. And then I take each of those three vectors and I add them all up, and I get a result, and I say, yes, now I know exactly how much force is on my charge up here. And then I walk out of the room, and Jorge comes up here with his charge, and he says, oh, and he puts his charge right here in the same spot. He says, I want to know what the force is on my charge now, right? And so he does the whole same thing again. And he has to work through it. F equals K, Q1, Q2 over R squared. And he figures the whole thing out again. And then he leaves. And Kelsey's like, hey, I want to know what the force is on my charge. She walks over and puts her charge in the same spot. And she has to do F equals K, Q1, Q2, all that same stuff again. You see how anytime we make a change, we have to start the whole problem over again, right? So I want to make a suggestion. And I want you to think about this between now and Monday, because we only have a minute left here. What I instead want to do is I don't want to put my charge right here. What I want to do is I want to take a very teeny tiny charge, because my charge actually might be big enough that it messes with and moves y'all's charge. But let's pretend I find this tiny little microscopic, tiny little amount of charge, like maybe even just a single electron, something really small that if I put here, y'all's charge doesn't matter, doesn't notice. Kind of like if I put a basketball near the sun's not going to notice, right? If I put a planet by it, the sun does notice. It will get wobbled. Earth does wobble the sun. But if I put like a basketball there, it's not going to notice, right? So I'm going to put a tiny little electron here. And I'm going to measure each one of y'all's force on it and it alone. And I'm going to get that force. And it's going to be K, my Q, which I'm going to call a test charge, that tiny little one. I'm just taking a test of it, times each one of y'all's charges, whatever they happen to be, right? We'll call it Q naught here, or we'll call it whatever, just Q. And we'll put this over R squared. And we'll do it the 3 times or whatever, but I'm just using that same little test charge. And I'm getting the total force on it. And then what I'm going to do is I'm going to take that whole thing, and I'm going to take that charge, and I'm going to remove it and get rid of it. And y'all don't even notice when it was there or when it was removed. So I'm dividing out this little test charge, which they're calling Q naught here. And it cancels out. And I end up with K, and then I'd have to do this for each one of y'all's, but KQ over R squared. And I end up with just that. All right. And say I did this for Michael's charge. Michael's was the only one in here. Okay. I did this for Michael's charge. So that Q that's left in there is Michael's charge. So I took Michael's charge. I measured his distance to this spot up here. I did Q over R squared times K right there. And now if I want to put my charge there, what do I have to do to find the total force of his on there? I just multiply my charge into whatever number I got there. Say it was a 7. So then I do 7 times my charge of 3. Hey, 21, I know the force on mine. And then I leave and Jorge says, I want to know mine. He comes up here, puts his charge here, he just says 7 times 4. Oh, 28, that's the force on mine. You see how he's not doing all of Coulomb's law over again? Because we came up with this number, K, Q over R squared, based on what his charge is and what location we were looking at. And we said, that right there, anytime I swap charge it, all I have to do is take the number I got from him originally and just multiply it by whatever new charge I got there, instead of redoing the whole problem every time. In fact, if I take and do it for his and Casey's and Van Van's and I add yours all up, I just get a number. All right, his was 7, yours was 15, yours was 3 or something, right? All right, we've got 25 now. I just bring somebody's up here, put it right here, multiply it by 25. Super easy, I'm done. I can start swapping charges out up here and know how to just solve it right away. Essentially, what we're doing is solving all of the problem except what we're going to change. And what we call this thing right here, we're going to call it electric field. It's the force per unit charge up here. It's the force per unit charge. And we can go around and do this, not just for this location, but we could take our little test charge and go around and map out this entire room or this entire space or wherever we need to, wherever we might be interested about where charges will go. And then we don't have to just plug it in here. We just come over to this one and say, oh, this is the electric vector that is there. That was the total from everything. I put my charge in, multiply it by the vector, I'm done. So F equals E times Q. Multiply the Q over to both sides, over to that side. You've got it, you're done. Change things out very fast. See how this is like a math trick? We're just doing all the problem that's not changing all at once, and then only changing out the part we need to change, right? And we're going to call this an electric field, and we will talk more about it. That's the basic idea. Think about this over the weekend. Make sure you understand and make sense to you. When we get back together, we'll start treating it as a real thing and what we can do with it, because it's very powerful. Have a great weekend.